Hi, welcome to Chem with Chem. This is the full workthrough of the CSEC Chemistry Paper 2 from the January 2019 sitting. Please like, share, and subscribe so you don't miss the other workthroughs. Also, check out the links below in the description of this video for other videos like this. Be sure to use the timestamps to toggle to your desired or favorite question. Have fun.
Now, question 1 is a data analysis question, as is normally the case, and we're being recommended not to spend more than 30 minutes on this question. Let's go. An experiment was carried out to determine the percentage of iron in an iron salt sample. A 0.500 gram sample of iron salt was placed in a conical flask. To it, 25 mils of dilute sulfuric acid, 10 mils of phosphoric acid, and 8 drops of an indicator were added. The contents of the flask were mixed and titrated against a 0.02 moles per dm cube solution of potassium dichromate until the endpoint was reached. The ionic equation for the reaction is given below. Dichromate plus 6 Fe2 plus, that's iron 2 plus 14H plus to give 6 Fe3 plus, 2 chromium 3 plus, and 7 moles of water. Figure 1 shows the burette readings of the initial and final volumes of each titration. All right, so we're asked a little later on to read and record the values from what is shown in figure 1 for the burette readings. So just to minimize us scrolling, we're going to just record these values from now. So we're just going to read them off and have them on hand, and then we're going to put them in our table on page 5. That's table 1. So we're just going to read these off. Then we're going to go back to part 1 where we list the apparatus that would be necessary to carry out the experiment. So we're looking at the burette here, and as is customary, whenever we have an instrument that has gradation and we're reading, we need to just figure out what the scale is, how much we're going up or going down by, what each of those little marks represents. So each of these little markings represents here 0.1 centimeters cube or 0.1 milliliters. So it means then that for the initial reading for titration 1, which is considered a rough titration, the initial reading, the reading there would be 2.00. And for the final reading in titration 1, we're looking at, this is 21.95. The initial reading for titration 2 would be, that's 1.85, and the final reading in titration 2 would be 21.85. That's right. Our meniscus, the bottom of our meniscus is in between the 8 and the 9. All right. The initial reading for titration 3 would be 1.50. It's sitting exactly on the 1.50 mark. And the final reading would be 19.50. So just make a note of those. We're going to, let us fix this so it looks like an 8. We're going to come back to these in short order when we fill out our table on page 5. Part A. So we're doing a titration. They already told us that we're doing a titration. They already told us that we're using a conical flask. And they're asking us to list the apparatus that would be necessary to carry out the experiment. They've given burettes already, or the diagrams of the burettes are, well, there's a diagram showing burettes, so I don't know if we should put burettes, if that is, if it's assumed that burettes are there. So we're going to list what the other materials that we would need in order to carry out this experiment. So we would need volumetric pipette. We're not just going to say volumetric pipette or just say pipette like that. All right, we have conical flask already. So it's fine, we don't need to put back conical flask. They said that conical flask is there. The contents of the flask were mixed and titrated. That's not where it was. Right, so they said it in the second line. 0.500 gram sample of iron salt was placed in a conical flask. To it, 25 mils of dilute sulfuric acid. Right, so we have the conical flask. So we'll need burette. We need a 50 mil burette, even though, you know, where burette is there, so it's a given. So we need a volumetric pipette. Conical flask is there. We're going to need a filter funnel. That's to fill the burette. We're also going to need a clamp and retort stand for the burette. All right, and that should be it. 2 marks. Okay, so the values that we just read off on the previous page for the burette readings, we're going to put them here, and we're going to find the volume of solution used in each case. So all the 6 values that we just read, we're going to fill them into our table. So use the information in figure 1 to complete table 1. All right, so in titration 1, the final volume was 21.95. The initial volume was 2.00, and the volume used would be final volume minus initial volume, and this would give us 19.95. In titration 2, the final volume was 21.85, and you can always scroll back to verify. The initial volume was 1.85. So 1.85 from 21.85 will give us 20.00. Titration 3, the final volume is 19.50. It can be read to 2 decimal places. The initial volume, 1.50. And so the final volume is 18.00. Now we get 9 marks for doing that. 9 marks, lovely. Part 1 of C, use an asterisk to, to indicate the titration data that should be used to obtain the average titration volume of potassium dichromate used in the experiment. All right, so normally when we're doing titrations, we want to get, it's great, it's awesome if we get identical values. That's not always the case. So we aim to get the next best, values that don't differ by more than 0.1. Now, looking at these 3 values, the variance between 20 and 18, that's big. So we would not use 20 and 18, despite them being consecutive. All right, so when we look, compare 20 with 19.95, those are close. Those actually differ by less than 0.1, which is great. So even though, you know, the first titration is normally the rough titration, as we saw on the page, the previous page, that titration 1 was the rough one, there's nothing that says we cannot use the values from titration 1. At the end of the day, it depends on the internal agreement among the values. And here we are, we're seeing where these 2 readings are close in that they don't differ by, they differ by less than 0.1. They differ by 0.05. So we're going to use those 2 readings, titration, the volumes from titration 1 and titration 2. So we're going to bear these 2 readings in mind, and we're going to apply it to the questions that follow. Part 2 of C, hence calculate the average volume of potassium dichromate used in the experiment and record the value to 2 decimal places. So that would be 19.95 plus 20.00. All of that added, then divided by 2. And our final volume is 19 point, or average volume, 19.98 centimeters cube, or milliliters, same thing. Part D, using the information from C2, calculate the average number of moles of potassium dichromate used in the experiment. The average number of moles. So we'll have to go back to the concentration of the potassium dichromate. So the average number of moles used, we'll have to use the average volume here that we got in part 2 above. And we're going to be working with the concentration of the potassium dichromate solution, which we know to be 0.02 moles per dm cube. The big M there represents molarity. So there's a formula for this, so we can just cite that formula and then we punch in our numbers accordingly. So the formula says moles is equal to concentration, which is in moles per dm cube, times volume. Concentration times volume. And volume here is in dm cube. So we'll have 0.02 moles per dm cube times, and we're going to be converting our 19.98 cm cube to dm cube by dividing by 1,000. So that would give us 0.01998 dm cube, 3.996 times 10 to the minus 4. Of course, dm cube would cancel out per dm cube, so our final answer, the unit for our final answer there is mole. So that's 3.996 times 10 to the minus 4 moles. Now, the next question, part E, says, from the equation given on page 4, determine the number of moles of iron ions, that's Fe2 plus, that react with 1 mole of dichromate ions. Now, we're just going to write down that equation so we don't have to scroll. So the equation said Cr2, so dichromate Cr2, O7 2 minus plus 6Fe 2 plus. We could pretty much stop there because the answer is there. Let's fix that. So that's 6Fe 2 plus plus 14H plus to give 6Fe 3 plus plus 2 Cr3 plus and 7 water. So we're concerned about, from the question, we're concerned about chromate and iron, the mole ratio of chromate and iron. So they're asking us to determine the number of moles of iron, that's Fe2 plus, that react with 1 mole of dichromate. So if we look to the left of dichromate, nothing is there. And if we see nothing there, it means that our coefficient is 1, or our stoichiometric value is 1. So just like in math, when it's 1x, we don't say 1x, we just say x. So we're seeing that for every For every 1 mole of chromate that is there are 6 moles of iron. So we just need to say 6 moles, and that would give us our mark. So that would be 6 moles. All right, so we're going to take these values that we have and we're going to apply them to the following question. So the next question, which we'll look at shortly, F says calculate the number of moles of iron in the iron salt sample. So we know the number of moles of, where is this now? We know the number of moles of dichromate that was used. Yes, we know the number of moles of dichromate that was used. We calculated that in part D and we got it to be 3.996 times 10 to the minus 4. And we said that for every 1 mole of dichromate, we had 6 moles of iron. The mole ratio of dichromate to iron is 1 to 6. So let's see what this would mean for our next question. So we just mentioned, or we just saw that 1 mole of dichromate reacts with 6 moles of iron. So the number of moles of dichromate that was used from our calculation in part D was 3.996 times 10 to the minus 4. So the number of moles of iron that's used in the sample would be the 3.996 times 10 to the minus 4 moles multiplied by 6, which would give us 2.3976 times 10 to the minus 3 moles. I could have rounded that. We could have rounded that to 2.4. Yeah, we could have rounded that to 2.40. All right. And then we move on to part G. Calculate the mass of iron in the iron salt sample. And they give us the molar mass for iron as 55.8 grams per mole. So mass, so this is a mole to mass conversion. So mass is equal to number of moles times molar mass. So it's a number of moles that we have in F, which is 2.3976 times 10 to the minus 3 moles multiplied by the molar mass, which is 55.8 grams per mole. So the per mole would cancel out the mole and would end up with grams. When we do that, we will have 0.13 grams of iron, Fe. Now, they want us in part H to calculate the percentage of iron in the iron sample. And if you recall, you can always rewind, you can touch it back to see the mass of the iron salt that was used. The mass of the iron salt that was used was 0.500 grams. And we just found that the mass from our calculations that, that was done using the titration, the mass was 0.13 grams. So to calculate the percentage of iron in the sample, it's the mass that we got, which is 0.13 grams, divided by the mass of the sample that was used, which is 0.500 grams. And we're expressing that as a percentage. So we'll have to multiply by 100, which would give us 26% for a mark. Part I, the reaction between iron and dichromate is considered a good reduction oxidation reaction. Define the term reduction in terms of electrons. So where electrons are concerned, we can think of redox, reduction oxidation. We can think of it as oil rig. So in this case, reduction is the gain of electrons. Part J, in the reaction, Fe2 plus acts as a reducing agent. define the term reducing agent. So a reducing agent is a substance that is being oxidized in a redox reaction. Substance that loses electrons and itself is oxidized in the redox reaction. That would give us our marks. So we're 3 marks away from 25 marks. And they want us now in K to calculate the oxidation state of chromium in Cr2O7 2-. Our rules for assigning oxidation numbers come into play here. Or not our rules, there are some guidelines that we use. Whenever we have a radical, this is a radical, a polyatomic ion, the sum of all the oxidation numbers must be equal to the charge that is on the ion. So when we take the sum, when we take 2 times the oxidation number of chromium and we add that to 7 times the oxidation number of oxygen, we must get -2. All right. So in this case, oxygen, as we know it, oxygen in compounds has an oxidation number of -2, except when it's in peroxides. Now, this is not peroxide, so we expect the oxidation number of the oxygen to be -2. So it means we can do a little, we can write an algebraic expression and we can solve for X, but don't be scared. So we don't know the oxidation number of chromium, so we can call the oxidation number of, we can let the oxidation number of chromium be X. So if the oxidation number of chromium is X, then we're looking at Cr2O7 2-. So it means, therefore, we can say that 2 times the oxidation number of chromium plus 7 times -2, which is -14. 7 times the oxidation number of oxygen, 7 times -2 is -14. So we'll just put -14 there. All of that is equal to -2, the charge on the polyatomic ion. So in essence, we're saying then that, hey, 2x minus 14 is equal to -2. All right, don't want to leave out any steps. So 2x minus 14 is equal to -2. So we're going to put all the like terms together. And when we do that, we would add 14 to both sides. Don't want to lengthen it, but just to show where we're going. When we add 14 to both sides, we're going to end up with 2x is equal to -2 plus 14 on the right side will give us 12. -14 plus 14 on the left side will give us 0. So we'll be left with 2x is equal to 12. If 2x is equal to 12, then it follows that x is equal to 6, but not just plus 6, positive 6 plus 6. That's the oxidation state. And part L for the 1 mark, that one is looking like the L. State 1 precaution that should be taken when carrying out the experiment. And of course, we will wear protective gears, such as our gloves and or goggles. Other one, care should be taken when working with acid. All right, and that would give us full marks, 25 marks. So that's it. Thank you for joining Chem with Chem.
Part A. Jamila is in her room studying and smells a scent of curry coming from her mom's cooking in the kitchen area. She thinks to herself, diffusion at work. Define the term diffusion. So diffusion is the movement of particles from an area of high concentration to low concentration until there is even distribution. Probably would have seen this before. or we could say movement of particles from where there are many to where there are few until there is even distribution. We'll stick to what we just wrote. Explain how the diffusion of the scent of the curry supports the particulate theory of matter. So in our answer, we have to state what the particulate theory of matter is. So of course, if we're smelling curry, it means some of the chemicals in the curry are in the gaseous state and would have diffused from one part of the house or the kitchen to Jamilia's room. So let's go. So gaseous chemicals from the curry diffuse from the kitchen to Jamilia's room, supporting that matter is made up of tiny particles which are always moving or which are always in constant motion. This reminds me of a program that used to come on early in the morning, Bodies in Motion. All right, okay, part 3. Diffusion is a process that can occur in liquids. State how the arrangement of particles in a liquid differs from that in a solid. The particles in a liquid are close together with small amounts of space between them. The particles can slide over each other. In a solid, they are very close to each other with little or no space. And in a gas, they're far apart with large amounts of space between them. Apart from diffusion, identify one process that supports the particulate theory of matter and state one example of such a process. Right, so we could, well, there are 3 processes that support the particulate theory of matter: osmosis, diffusion, Brownian motion. Osmosis is a special type of diffusion. So we can say osmosis, and an example would be peas, and we will say quote unquote, swelling when soaked in water. Not just peas. It happens with saltfish. It happens with raisins in water, right? And we could also use Brownian motion. And an example is us seeing tiny specks of dust particles moving about in a crazy manner. When you turn on like the projector, that would probably take a few more lines. So we'll work with what we have here. Part B. Jamilia's mom showed her that in order to cook with curry, she first had to mix the curry powder with water. Really? We don't. Right. Jamilia observed that the mixture resembled a chalk and water mixture she had seen in a class, except the curry mixture was brown. Part 1. State whether the mixture of curry powder and water is a suspension or a colloid. All right. So if it resembles chalk, if it resembles a chalk and water mixture, then it is a suspension. And if it's a suspension, then the most appropriate technique that could be used in the lab to separate this mixture is filtration. because the particle size, the solute particle size, or the solute particles would be big enough to actually be trapped in the, or be trapped by the filter paper pore. They would not be able to pass through. Still questioning that mixing the curry in water. I'm not sure where we do that, but yeah, let me leave it there. Part 3. Draw a clearly labeled diagram of the apparatus that could be set up in the school laboratory to separate the mixture of curry powder and water. In a diagram, show the location of the separated components. All right, so we just need to draw the setup for filtration. So we'll need our filter funnel. And you'll be using a ruler to do this with a pencil, so your lines would be straight. That's our filter paper. This is our flask collecting the filtrate. So let's label. So this is our residue, which is the curry powder. So let's go. So first, this is the filter funnel. This is our filter paper. That's the curry powder, which is our residue. This would be a conical flask. The filter funnel would sit nicely on that. And our filtrate, the liquid, the water in this case, that goes through the filter paper pores. So the filtrate would be water, or we should say water and put filtrate in bracket. So this would give us the 4 marks. Of course, you'd use your rulers and your pencils, so your diagram would look nice. And just like that, you just got 15 marks. Just looking at this, we're seeing energy coming up and what a time it is. Oh my word. Organic chemistry, it is. Compound A is a straight chain hydrocarbon with the molecular formula C5H12. Part 1. State 1 natural source of hydrocarbons and 2 possible uses of compound A. Now we're going to just list out all the natural sources. Over answering, if we get a question like this, we would just give one. But the natural sources are naturally natural gas. Well, it's not called naturally natural gas. Natural gas, crude oil. Crude oil is also called black gold for obvious reasons. Crude oil is another name for petroleum. And another source is biogas. And this compound here with the molecular formula C5H12, I think it's something we've seen already. That is pentane. That looks like, that is coming from the alkane series. Now, a use of pentane could be used as can be used as a fuel. It can also be used as an organic solvent, where it can be used to dissolve non-polar substances. So that would give us 3 marks. Part 2, draw the fully displayed structure of compound A. So the molecular formula is C5H12.
This is a saturated hydrocarbon, so we'll draw our 5-carbon skeleton and we adorn them with the hydrogen. In a deja vu moment here, the more we practice, the more this thing just becomes second nature. Even drawing will be muscle memory. So here we go. Each carbon must be taking part in 4 bonds. So that's that. And 2 more marks. Part B. 1. Thermal and catalytic cracking are very useful processes in the petrochemical industry. Define the term catalytic cracking. So let's just get right into it. Don't want to use but the word cracking. We probably over answered part 1 a little bit by putting in more useful. It's the breaking up of long chain hydrocarbon compounds into smaller hydrocarbons using a catalyst or into shorter chains. And the importance of catalytic cracking in the petroleum refineries in part 2 here is that the smaller or the shorter chain hydrocarbon compounds are more useful. So we'll just state that smaller products or smaller chain or shorter chain hydrocarbon are more useful. So they're easy, they burn more easily, right? So diesel doesn't burn as well as octane. So that the heavier the fuel or the longer the chains, the longer the fractions, the harder it is for them to burn. So they would not be very good accelerant. So kerosene burns easier than diesel, which still burns easier or more easily than heavy fuel oil and so on. So that's it. 3 more marks. Part C. Another hydrocarbon, compound B, with the formula C5H10 can be converted to compound A in a simple one-step reaction. Part 1. Draw a possible fully displayed structural formula of compound B. C5H10. This is similar to the one we saw earlier. This is similar to compound A. Compound A we said was C5H12 and B is C5H10. And the difference here is just 2 hydrogens. And they're saying that B can be converted to A in a simple one-step reaction. Now, what would the fully displayed structural formula of compound B look like? Well, in order for us to get a compound with this formula, it means that there will have to be a carbon-carbon double bond. So in compound A, we said that this was saturated. Compound B is unsaturated. So we'll still have 5 carbons. So let's go, but somewhere in the mix, we're going to have to put on a carbon-carbon double bond. You could put it between carbon 1 and carbon 2, or between carbon 2 and carbon 3. So in this case, I'm putting it between carbon 2 and carbon 3. And you're probably saying, but how come? It's because I'm counting from the right-hand side. You can count from any side. right? So we want to ensure that each carbon is taking part in 4 bonds. And we put on our hydrogens. That's it. And they want us to, in part 2, state one physical property common to both compound A and compound B. All right, so physical property. So they would be both liquids. That's one. And we could also say, so a second one, they do not dissolve in water. And that would give us 3 more marks. How many marks have you gotten so far? At the end, please say how many you got out of the 15. Part D, last 4 marks. So we've gone 11 so far. Compound A and B can be distinguished by reacting them with bromine solution in the dark. Part 1, state which of the 2 compounds, A or B, reacts with bromine. So just a reminder, compound A is C5H12 and B is C5H10. All right, so A is an alkane. I mentioned that at the beginning. And B is an alkene. Now, the one that reacts with bromine solution in the dark, it would be the alkene, which is compound B. State the color change that is observed when the reaction occurs. That's part 2. Well, when we're given a color change, we have to state the former color and we have to change the final color. Former state, final state. So we don't even have to write this in a sentence. We'll just say brown to colorless. So alkenes will decolorize bromine water, but you have to state, or bromine solution, but you have to state the initial appearance of the bromine water or the bromine solution. And they want us in part 3 for the last 2 marks now to make it up to 15 to write a balanced chemical equation for the reaction. So I'm going to be consistent. I'm going to use the same formula, same displayed formula I used earlier on, where the carbon-carbon double bond was on carbon 2. So we're going to draw out everything so we can see what is happening. We'll need as much space as possible. So let's go. So this is compound or alkene. 1, 2, 3, 4, 5. So this would be pent-2-ene, or some books will say 2-pentene. But convention says pent-2-ene, but anyway, doesn't matter. So that's our compound B. And this now we would add, it's an alkene, so we know alkenes undergo addition reactions, and we would be adding across double bond. So let's use something different for the bromine. So this is Br2, and that's a liquid, and the condition we're going to be using there is CCl4 because it's bromine solution. So bromine would be in tetrachloromethane. Like dissolves like, tetrachloromethane is an organic solvent, which is nonpolar. So it would dissolve bromine, which is nonpolar, like dissolve, like dissolves like. So the final thing, we put space, but we're going to see if we can scrunch it up here. 1, 2, 2, 3, 4, 5. This should do. So right between, let's highlight it. So just keep looking right there. Goat. All right, so we're gonna zoom in on the same area. in a little bit. So let's put on back the hydrogens. Okay, what did we do? Need back our pen. All right, hydrogen, 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 hydrogen. Okay, so let us switch our here. That's where we're focusing on. All right, so right where the carbon-carbon double bond was, we're just going to break one of them. And when that happens, it means that each of those carbon atoms that was, sharing the carbon-carbon double bond will now be able to take on a bond with the bromine. So we say we're adding bromine across the double bond. So since we had the bromine in black, we're going to put them on in black. So this is what we would have as the final product. And just like that, you got 2 more marks. Now, this question is very special because this question spans all of 4 topics. How did they do it? How did they get 4 topics in one question? So preparation is key. All right, let's get into it. Can you state the 4 topics that you see here? If you can spot them, just put them in the comments. Say what you think the topics are. So let's get right into it. We want to go as fast as well as quickly as possible without compromising quality. So let's go. All right, so 4A, define each of the following terms. So part 1, the first one, atomic number. Atomic number refers to the number of protons in an atom of an element. Mass number, this refers to the sum of the protons and neutrons in an atom of an element. Part B, sodium is a metal with an atomic number of 11 and a mass number of 23. Part 1, draw a diagram to show the arrangement of electrons in a sodium atom. All right, so it's very important. They've given the mass number, so it means that we're going to use that to figure out to determine the proton number. So we will need to state 11 p's in the center, 11 p's, 12 n, it's 12 neutrons. That's how we will get 23. Let's make that clear. Then normally put a little circle to show that that's the nucleus. And we're going to be putting our 11 electrons. 2 on the first shell, 8 on the second shell, 8 plus 2, 10. The 11th one on the third shell, 2, 8, 1. Part 2 of B, state the period to which the element sodium belongs in the periodic table. So we just mentioned 2, 8, 1. So that means we have 3 electron shells. So it means it would be in period 3. Describe the type of bonding in sodium metal. So it's sodium metal. So they're talking about metallic bonding. So we're going to just get straight to the point. We would have sodium ions, also known as cations. They're positive ions or they're positively charged cations. And so these cations or these sodium ions are embedded. Keyword there, embedded. Some students will say stuck. They're embedded in what is called a sea of mobile, or let's say delocalized electrons. Students said that word last year and I got very excited. So that would give us full marks. Part C. Sodium chloride is a typical salt of sodium metal. A concentrated sodium chloride solution, brine, can undergo electrolysis when it is used as an electrolyte in an electrolytic cell using inert electrodes. Part 1. Define the term electrolysis. Right? Whenever it comes to defining terms, I love to look to see what the words are coming from. If you look at the word electrolysis, you should be seeing two words, electro and lysis. Electro coming from electricity, and lysis, for those who do bio, you would have seen lysis several times. Lysis means to split. So it's pretty much using electricity to split something. So let's lotion that up. So we'll say it's the decomposition of an electrolyte by the passage of an electric current through it. So let's get that down. Two marks. Part 2. Write the half equations including state symbols for the reaction that occurs at the anode and cathode during the electrolysis of concentrated sodium chloride solution. That's brine. You guys would have come across brine already. Tuna in brine, mackerel in brine. So whenever you see brine, it's concentrated sodium chloride solution. All right, anode. So the ions that we have are definitely Na plus, aqueous. Would also have Cl minus, aqueous. Would have H plus from the water. Would also have OH minus from the water. Now, generally, OH minus ions would be liberated. Well, we know that the chloride and the OH minus ions would migrate to the anode. So to be on the safe side, I normally put the sign beside the electrode so I know exactly what ions should go over to that electrode. So the chloride and the hydroxide would migrate to the anode. But because we're talking about concentrated sodium chloride, it means that we have a relatively larger amount of chloride ions than OH minus ions. So in this case, instead of the OH minus ions being liberated or being given the nod to be set free, the chloride ions would be given the nod. So chloride would actually win in this case, and that would give us 2Cl minus aqueous, liberating or giving chlorine, Cl2 gas, plus 2 moles of electrons. And over the other side, even though we have a relatively higher amount of Na plus, we had said in previous session that breaking up is hard to do. So the sodium would not be liberated preferentially to its counterpart, the hydrogen, the H plus ions. It still takes too much energy to actually pull apart or break up the Na plus ions from the chloride ions. So in this case, the H plus would be given. The sodium is higher in the reactivity series. So in this case, it would require too much energy to actually break apart the ions. So sodium ions would be liberated. So in this case, the H plus would be given the nod. So please note how we write reduction plus electrons, and we end up with the hydrogen gas. And we write oxidation We have the species being oxidized, then the arrow. So we must end up with, when we put the two equations together, we must end up with electrons on the right-hand side and electrons on the left-hand side. And that's how we actually cancel them. But we're not going to cancel them out right now. All right. So this would give us full marks, and nothing else is asked here. So that is it. We just need to give these half equations, state symbols, ensuring that they're balanced, and we're good to go. And just like that, you got 15 marks. So please leave your comment. What 4 topics were covered in this question? Write them. Let's see how sharp you are, how much you're spotting your questions. You're studying chemistry, but we have to break it down in modules, and in topics, then in subtopics. Let's see if you can spot the topics that were covered in this one question. This question is on organic chemistry, introduction to homologous series and reactions of organic compounds. Part A. Methane is the first member of the alkane homologous series. 1. List 3 general characteristics of a homologous series. They have the same general formula. They have the same functional group. They also have the same ending name. Part 2. Write the molecular formula of the second and third members of the alkane homologous series. So they've given us the first one, methane. So they want ethane and propane. So for ethane, the second one, it would be C2H6. And for propane, it would be C3H8. From this now, in part 3, we're asked to derive the general formula of the alkane homologous series. If you know it, you could just write it. But just looking at what we have here, C2H6 for ethane, C3H8 for propane, we're seeing that for the number of carbon atoms, we're seeing that the hydrogen atoms is twice the number of carbon atoms plus 2. So from that, we could write CnH2n plus 2, n representing the number of carbon atoms. 2 2's 4 plus 2, 6. 2 3 6 plus 2 8. Part B. 1-butene belongs to the alkene homologous series and exhibits structural isomerism. Part 1 of B. Define the term structural isomerism. This is the existence of organic compounds having the same molecular formula but different structural formula or different arrangement of the atoms in space. Let's get that down. Part 2 of B. Draw a fully displayed structural formula of 1-butene and its 2 isomers. All right, so we'll do 1-butene, and the 1 there is telling us that the functional group, which is our carbon-carbon double bond, is going to be found at the first carbon. Whether you want to count from left to right or right to left. But naturally, we read from left to right. So I'll put the carbon-carbon double bond at the first one from the left. All right, it doesn't mean that you couldn't put it on the first one from the right. So I'll put, so let's go. That's first carbon, that's a carbon-carbon double bond. But means 4. Let's adorn or put on the hydrogens on our carbons now. each carbon must be taking part in 4 bonds. Carbon is tetravalent. Tetra means 4. Valence having to do with the valence electrons, electrons in the outermost shell. So that is that's 1 butene. And we could have also drawn it, we could have flipped it around, in which case the carbon-carbon double bond would be still at carbon 1, but from the other side, same thing. There we go. That's what it's the same thing. Same thing. So these two are the same thing. I just wanted to make that clear. All right, so let's look at an isomer now. So to get an isomer, we want to each time rearrange this so we get a new form. All right, and please look out. You can just check the card, the description above, for a video that will look at some of the common terms that are often confused, like isomers versus isotopes. So you can just check that out. If it's not there, you can just look back in a few days and it will be there. So just check that out. So we could take the carbon-carbon double bond and we could put it at carbon 2. And this is what the skeletal structure, the framework would look like. So carbon 3, 3 carbon, carbon 4. And again, we want to ensure that each carbon is taking part in 4 bonds. So there we go. So this is isomer 1. They didn't ask us to name it. Perhaps they'll ask us to name it in subsequent questions. And then we want to do isomer 2. So what we're going to do in order to get isomer 2, and I'm going to be using the one that I did in blue up top to illustrate. So we're going to let everything remain, but what we're going to do, we're going to cut off this portion right here. We're going to cut off this methyl group, and we're going to trade places with this hydrogen that's, let's call this carbon 1, carbon 2, carbon 3. We're going to trade places. We're going to take this methyl group, and by methyl group, I mean the CH3 group right here. We're going to take it and we're going to trade places with the hydrogen. And that will give us a new form, same molecular formula of C4H8, but the atoms are arranged differently in space. So when we do that, this is what things will look like to give us isomer number 2. So this is what we'll have. So let's put on so this is in the middle, carbon 2. We're putting on the methyl group. So that's CH3. We're going to just draw it out, all fully displayed. And we swapped places with the hydrogen. We're putting that back on. And we just need to put the 2 hydrogens on this carbon and we are good to go. Right? So 1 butene, 2 butene, and 2 methyl propene. All right. Part C. Will remain in few marks to make it up to 15. 1 butene, like all alkenes, are described as unsaturated compounds and undergo hydrogenation reactions to become saturated. Define the term unsaturated. So unsaturated means that there is a carbon-carbon double bond, or unsaturated means that the compound doesn't have carbons that are only taking part in carbon-to-carbon single bond, or carbon to carbon single bond. So unsaturated, let's just get that down. Part 2, State what is meant by a hydrogenation reaction. And if you look carefully, if you break down the word, you'll see hydrogen in the word and you'll see ation. So all it means is it's a reaction where hydrogen is being added. So it's So it's a reaction where hydrogen is being added to the alkene, and they want us to draw the fully displayed structural formula of the hydrogenation product of 1-butene, 1-butene. So let's just remind ourselves of what 1-butene looks like. Oh, this is not the answer. We're just reminding ourselves of what 1-butene looks like. So if we're adding hydrogen, then the hydrogen is going to be added across the carbon-carbon double bond. So we'd cut one of these bonds right here, which would now make room on carbon 1 and on carbon 2, or the hydrogen that we're adding. So the hydrogen, one of the H's would go on carbon 1 and one of them would go on carbon 2. So it would give us our final product, which would look like this. So it would move from an unsaturated compound to a saturated compound. So we could put a hydrogen here, could put one here. And they're all identical, but I just wanted us to be able to spot where it actually was added. So this is the final product, and that would give us the full marks. And I'm just going to highlight it by putting it in a box. So that's it. Question 6, part A. Carbon is found in the form of diamond and graphite and is a main component in many naturally occurring compounds such as organic matter and carbon dioxide. State one way in which diamond differs physically from graphite. Right, so we should be thinking allotropes, allotropes, allotropes. So one way in which diamond is different from graphite, let's just get that down. So it's all in the appearance, not just the appearance, but graphite is a black solid while diamond is a sparkly glass-like hard solid. Sparkly things, right? Part 2, state one similarity between diamond and graphite other than they both contain carbons. Okay, so similarity, they both have high melting points, so we could say they have high melting points. Could also say that they are giant covalent structures, or they have giant molecular structures. We could also say that they're solids. All right, so we have a few options there. Part B, carbon can react with a limited supply of oxygen to form carbon monoxide, which can negatively affect human health. 1, write a balanced chemical equation including state symbols to show the formation of carbon monoxide. All right, so this is carbon, solid, burns in oxygen, but limited supply, and that would give us carbon monoxide, CO, which is a gas. And of course, we would have to balance. We have 2 oxygen on the left, 1 on the right. So we put a 2 on the right to make the 2 oxygen on the left, 1 on the right. So we put a 2 in front of the CO to ensure that the oxygens are balanced. In doing so, we now have 2 oxygen on the right and 1 on the left. So we put a 2 in front of the carbon there, and we're fine. Part 2, state 2 effects of carbon monoxide inhalation on the human body. All right, so we get severe dizziness or severe headaches, dizziness, drowsiness, and it can result in heart attack. So many times when there are fires, it's not that persons would just, die from burning. Most of the times it's carbon monoxide poisoning, which causes them to become unconscious. And then because they're knocked out or they fall down, they end up being burned, So tests normally show when they do the post-mortem analysis, they normally find that, they look at the cause, manner, mechanism of death, you realize that, it's not really the burning that really killed them. It's really, they would have been dead before, or it would have been as a result of carbon monoxide poisoning. They would find cherry red blood and all of that. But right, you'll go deeper into that when when you go to med school or you do forensics. Part C. Jamal wants to prepare and collect a sample of carbon dioxide gas in the laboratory using calcium carbonate. Part 1. Write a balanced chemical equation including state symbols for the laboratory preparation of carbon dioxide gas from calcium carbonate. So calcium carbonate is a solid HCl aqueous, that's an acid. That would give us calcium chloride, that's CaCl2, carbonate. So this is aqueous. Carbonate plus acid will give us salt, water, H2O liquid, and carbon dioxide, CO2 gas. So now to balance. We have 2 Cl on the right, 1 on the left. So we put a 2 in front of the HCl. And that should do it. That should give us 3 marks. Part 2 for 3 marks. Draw a clearly labeled diagram to show the arrangement of the apparatus and materials that could be used in the laboratory to prepare and collect the carbon dioxide gas. All right, so we're using the reagents that were mentioned above, calcium carbonate and HCl. All right, so a few things to bear in mind that will determine the type of apparatus we use. Carbon dioxide is denser than air, so we'd have to use the upward display. We'd have to use a technique that would result in the upward displacement of air. It's soluble in water, so it's best if it's not collected over water. All right. And in terms of collection as well, we don't want to dry it with calcium oxide because calcium oxide is basic. Carbon dioxide is an acidic gas. It's an acid anhydride. So it would react with the calcium oxide. So that will kind of govern how we go about collecting, what we use for drying, and the type of delivery. So let's see if we can get the apparatus on this. All right, so let's see if we use black for drawing. All right. So this is our flask where the reaction is going to take place. judge the straightness of my lines or the lack thereof. It comes down to device. But of course, on flat paper with pencil and rulers, your diagram should be neat. All right, so here we're going to have marble chips, or what we call calcium carbonate. So marble chips go here, marble chips. Then, of course, this is a thistle funnel. We've seen this before. So this is a thistle funnel, THISTLE. It's a thistle funnel, and 8Cl is contained here, and there's a stopcock so we can open to release. So we would need a delivery tube now. And then we would definitely need to close the system so the gas doesn't escape. So that's your rubber bone. So our delivery tube will go down into a U-tube, not the medium that you're watching this on, but you can see why they call it a U-tube. It looks like the letter U. All right, so this is our U-tube. Then we're going to seal, of course. So this is sealed here. We don't want the gas to escape. And then we'll have another delivery tube. Space is a bit limited for the drawing, at least based on what I'm using. So this delivery tube goes down into our gas jar. As the carbon dioxide goes down, air is displaced up. So we say it's the upward displacement of air. But the delivery of the carbon dioxide is actually downward because it's more dense than air. As it goes down into the gas jar, then the air would be displaced going up. So we call it the upward displacement. But the delivery is downward. Delivery of the carbon dioxide is downward. All right. So in this U-tube, we would have anhydrous calcium CaCl2, calcium chloride. That's our drying agent for the CO2, because we don't want to use calcium oxide, which would react with the CO2. So this is our CO2. This is our gas jar. What else? Of course, these are delivery tubes. Okay, let's see if we can get the writing more legible. All right, that should be it for 3 marks. Part 3, for the last mark to make it up to 15. State one use of carbon dioxide as it relates to the beverage industry. All right, and we love this. It's used to give or to make the fizz in drinks. We know about fizzy drinks, carbonated beverages. That comes about because carbon dioxide would have been pumped into the drink under pressure. So that's what gives it the fizz. And we love the fizz, but it's a nice way to mask the sugar that is actually there. So if you were to shake up the soda, cause the CO2 to be released and the drink becomes flat, then you would get a better idea of how, I don't want to say insipid, but how much sugar is actually present. So it's a marketing strategy that has been employed over the years to really hide the sugar. We're distracted with the fizz. We get caught up with the fizz. Kids love the fizz. Everybody loves the fizz. But it really hides how much sugar is there. But anyway, let's just answer the question. So it's used to give the fizz in drinks or in carbonated beverages. So that's CO2. We don't necessarily need to put this part here. That would give us 15 marks. So please state in the comments how much you got out of the 15. I hope you're sharpening up your skills. Remember to like, to share the video, and if you have not subscribed, to do so and to turn on post notification by hitting the bell so you're updated each time new material is added. So this has been another session on Chem with Chem. See you in the next video.